In this video we're going to go over the trajectory of a particle under the influence of the Earth's gravity. So if we start off with our coordinate axis, so we'll call that our y-axis, and we're going to do it not in terms of our time here but in terms of our distances. So we've got a y-axis and our x-axis, and imagine if you're throwing up a ball, the ball's going to go up and it's going to cover some sort of path like that. Okay, so we know that the Earth's gravity it's a conservative force, so we can say that the kinetic energy plus the potential energy is a constant. Okay, so we can use the principle of least action, which we talked about in a previous video. So we can say that if we work out twice integral from, say, point A to point B, so that's point A there and that's point B there, of the kinetic energy by dt, that's going to equal some constant, or it's going to equal a value I, and I is going to be a stationary value. Okay, so we went over this in the couple of videos ago. Okay, stationary value. Okay, so let's put the values in and we'll work through this, and we'll work through using the Lagrangian method. So if we say that kinetic energy T equals a half mv squared, now we can write the instantaneous velocity v equals ds by dt, because we're going to get all this here in respect to a distance ds as opposed to dt. Okay, so we can then say that our ds equals v times our dt. So then we can say that 2 times the integral of a half mv squared by dt from a to b is same as saying the integral from a to b of our mv squared by dt, just cancel out the 2.5. So that's going to equal the integral from a to b of our, well, v dt is taken up by one of the v's here in dt, so you're going to be left with 1v, and if we assume that m equals 1 for the moment, then you're just going to be left with your v ds. Okay, so that's m equaling 1. Now we're going to get in and we're going to look and see what this v is here and what the ds is in terms of our little drawing up here. Okay, so now the ds is going to be a small element on the path. Okay, so that's a small element, so each of the small elements on the path, and the v is going to be the velocity which is in the direction of the travel. Okay, so it's going to be the velocity is going to be the tangential component. Okay, so we've seen this before a few times now, so we can write the small displacement ds squared in terms of our dx squared plus dy squared. So all we're looking at is a small element in here, and it's got a dx term and it's got a dy term, and the element there is your ds. Okay, so we've got that there. So what we can do is we can divide throughout by dx squared, so you end up with ds squared upon dx squared. It's going to equal, well, that will be 1 plus, and we'll just use the y derivative term, y derivative squared. Okay, and okay, so that's that part there. And so then we can say that if we take the dx up, we can say that our ds squared is going to be 1 plus our y derivative squared all times our dx squared. So then we can say that our ds is going to equal 1 plus y derivative squared, and it's going to be the root of that, so it's to the power of a half times the root of dx squared, which is just going to be our dx. Okay, so that's one part that we're looking for our ds. Now the other part we're looking for is our velocity. Now we can get our velocity from the usual equation that you have seen, v squared equals u squared plus 2as. Okay, so that's the velocity in terms of your initial starting velocity, the acceleration, and the displacement s. Okay, so you notice that time is nowhere in that equation. Okay, so we can then say that v squared is going to equal u squared plus 2, and of course acceleration is acceleration due to gravity, and the displacement, well, the displacement is just given by your function y of x. Okay, so because y of x will give you your height with respect to your movement along the x-axis, so that's just going to be that displacement. And now notice as well that gravity acts down the way. Okay, so in this case we'll say it's minus g, so there's going to be a minus term added in there, so you're going to end up with your v squared equals u squared plus, that's actually minus, let's put that in, there was no point in saying that. Okay, so that's going to be minus 2g, and I'll just put y, I'll not put y of x because it's understood that it's y is a function of x. Okay, so that's our second little part. Okay, so we can call that one 2, and we can call that one 1. Now we're going to put these in for our VDS, so you're just going to have the integral from a to b over u squared minus 2gy all to the power of a half times 1 plus y derivative squared to the power of a half times ds. Okay, so that's us just put our two equations in, so we've got our 1 plus y derivative to the power of a half in here, and of course we've had to take the root of that to get the velocity, because that's in terms of velocity squared, that's why we've got our root point, root there. So that's our little equation that we're going to start off, the Lagrangian equation here. Okay, so now what we'll do is we've noticed that there is a function of y and y derivative. It's not directly a function of, implicitly a function of x, so we can use that Beltrami identity. So we can say that the Euler-Lagrange will simplify to f minus y derivative partial f by partial y derivative equals a constant. Okay, so that's what we're going to use, and we're going to stick our Lagrangian term here into this here, and we're going to mess about with it till we get our function y of x. Okay, so let's just go ahead and we'll go and get that done just now. So the function can be written as, now I'll simplify this out a bit as well so it won't look quite as bad, as u squared minus 2gy to the power of a half times 1 plus y derivative squared to the power of a half, that's the f part, minus y derivative times, well, it's partial f by partial y derivative. So the only part of this equation here that's got any functional of y derivative is this part here. So this whole thing here is just going to look like a constant. Okay, so you're just going to have your u squared minus 2 gy to the power of a half, and whenever you differentiate that there, if I can get it all into the line, so you're going to have a half times, so you're going to have, I might be able to squeeze this in, but a half times 1 plus y derivative squared, okay, to the power of minus a half, and then you have to derive what's inside it, so you're going to have times 2y derivative, okay, and with all that thing there equals some constant c. So bit of a monster equation, but we'll simplify it out. So what we'll do is we'll call this first term a, okay, and we'll call this second term here, we'll call that b. So we can say that a times b minus y derivative times, well, it's going to be a for this term here times, well, that's going to be 1 upon 2, and that's b, but it's b to the minus a half, okay, so it's equivalent to 1 upon b, so you could write that as 1 upon 2b, and that's all times 2y derivative. 2y derivative equals some constant c. So all we need to do is do a wee bit of messing about with that there. So we can say that a times b minus let's see, y derivative, and you're just going to have a times 1 upon 2b times 2y derivative. I've actually written this one out already, equals c. It's the same as that line up there. So we're going to have a times b minus, well, it's going to be 2y derivative squared, okay, because it's y derivative times the y derivative times our, and it's just going to be a upon 2b, a upon 2b equals some value c. So therefore we can say that c equals, if we take a common denominator of 2b, common denominator 2b, say what do we do to that value there to get 2b? You have to multiply it by our 2b, so you're going to end up with our 2ab squared minus 2y derivative squared times our value of a. Okay, so we're just taking our common factor there of 2b for both this point, this numerator, and that numerator as well. So that gives us our a times b minus, and I'll just get rid of the factors of 2, we don't need them because there's factor 2 in both the top and the bottom. So we've got our a times b squared times minus our y derivative squared a all upon our value b, which equals our a b squared, just take out the common factor of a there, a b squared minus y derivative squared all upon, now we'll put our value back in here for our b, so our b is our 1 plus y derivative squared to the power of a half. Okay, so if we were to rewrite that out and put our a's and b's back in, we're going to end up with our value. So our a is going to be our u squared minus 2gy to the power of a half times, now it's going to be our b squared. Now our b is our 1 plus y derivative. If we go back up there, our b is our going to 1 plus y derivative squared to half. So when we square that, we'll just have 1 plus y derivative squared. So we're just going to have that, and it'll be 1 plus y derivative squared for this b squared term here. But now we're taking off minus y derivative squared. Okay, so we take that away for that, we just end up with 1 there. So it's all of that over this 1 plus y derivative squared to the power of a half. Okay, so we cancel that with that, so we just end up with our final equation there, which is u squared minus 2gy to the power of a half all upon 1 plus y derivative squared all to the power of a half. Okay, and that there equals C. Okay, so I'll put a wee circle around that. That's actually, if you are having a look at that Fox book, that's actually in the book there, so that's the derivation there. Of course, he doesn't do any of that derivation, it just jumps from one line to another, so it's good to see it done. Now we're going to transpose this for y derivative squared, so you can square both, you can make that c squared, we can square both ends there, so you end up with our u squared minus 2gy right upon 1 plus y derivative squared equals c squared. Now if you work through that, and you've got to take the 1 plus y derivative squared up, multiply it by c squared, okay, and then you can take the other c squared back over here, and eventually you can get your y derivative squared. I'll just write it out because it's easy enough to transpose that, so we just end up with 1 of y derivative squared equals, now here is a little thing that you can maybe check yourself. I get it equal 1 upon c squared, it's going to be u squared minus 2gy minus c squared. Okay, so that's the equation that I get. Okay, but the book, so when I do that derivation, that's what I get there. Okay, but the book doesn't have it written like that. The book has it written as c squared is on the top line there. So what I'll do is I'll work through and continue with it as per this derivation that I have. Okay, so you can always go through and see if you can see where I've maybe made a little mistake there, but possibly there's a typo in the book. So what we can do, we notice that in this little differential equation, a quick way of solving it, I noted is if you look on the right hand side here, you're going to have this is a little constant, that's a little constant as well. We know it's velocity anyway, that velocity and it's squared. Well, g times y, well, gravity is in units, it's going to be mass meters per second squared times y, which is meters, so it's going to be meter squared when second squared, so that's going to have units of velocity squared. Okay, so the right hand side here has got units of velocity squared. Okay, so it means that we can write the right hand side here is y derivative squared equals, now in the units of velocity squared it's going to be gravity, okay, but it's going to be gravity times, and it'll be another, again it'll be a distance in meters. So if we write the distance meters as you can write x minus x naught, okay, so it's a difference, okay. So but in the book they use the term d, okay, so we'll just use what we've got in the book. So we've got g of x minus d, so this side here has got units of velocity squared, but we're not looking at just y derivative, the y derivative, we're actually needing the y derivative squared. So the y derivative squared is going to be your g squared, is going to be x minus d squared. Okay, so that means that we can finally write out, and I've just got enough space here. In fact, I'm maybe, let's see, well, I've just enough space here, I'll just write it down the bottom. So you end up with our value of our, what is it, c squared u squared minus 2gy minus c squared equals our value g squared x minus d all squared. Okay, so I'll put a bracket in that because that's the equation that's been derived in the Fox book, which I'm covering. Now, you may have noticed a little cop out there. As I said before, I've done this derivation and I've got it in terms of 1 upon c squared there, but the actual derivation, the final derivation they work out is c squared here in the top line, so I'm not sure where that anomaly comes in. I'll check through again at some point and see if I can find it and put a note at the bottom of the video. So now, just to show that this actually works, what we can do is we'll look at it in a little tool here. Now this is an online graphical calculator, so if I can bring it up here, let's see, so that's it there. So I've stuck the equation in to this tool. It's called Desmos, D-E-S-M-O-S. So there you go, c squared, you can see it in the top line up here. We've got c squared equals u squared minus 2gy minus c squared equals g squared x minus d squared, and I've put in the values here. Now our initial value for our u, initial velocity, is 10 meters per second, so it's 10 meters per second, and I've put it, fixed it out. The value of c here adjusts the angle, so set it out at an angle of 45 degrees just as a check and see that the equation actually works. So at 45 degrees it should travel its furthest distance, and the gravity is 9.81, and you can see that the distance here that's travelled is actually 5. Let's see, it's 10. The distance travelled here is going to be 10. Okay, just see what it's 10.2. Okay, so if that's right, then we know it's right. We can do it quite quickly because if we go back here to our smooth draw here, I'll just find a little corner here. If you look at equations of motion or projectile motion, you can say that the value d, the distance travelled, when you're sitting at 45 degrees, it travels its furthest distance, and the distance should be the initial velocity squared upon the gravity. Okay, so initial velocity squared, that's 10 squared upon 9.81, which is approximately equal to, it's about 10.2 meters. Okay, so you can see that the equation, if I go back into Desmos, the equation does indeed give us the correct value, so it's about 10.2 meters. And you can see as well that all d does is just change the starting point. Okay, so if you shift d about, you can see it just shifts the starting point here. Okay, and the value of our u changes our initial velocity. Okay, right, and the value of our c will change our initial angle. You can see it there, and you can see that at 45 degrees it's roughly 45 degrees there, but when you go beyond it, you can see the distance dropping off and drop off and drop off. Okay, and distance increasing to a maximum and then dropping off and dropping off. Okay, as you'd expect. So the equation does work. So that's all for that one, and I'll move on to looking at another example. Okay, thank you and goodbye.